What's up my friends, welcome back. So today we have a different video. I know that a few days ago I posted on the community tab that we will have a live session, a live stream, but for me it's a little bit difficult to make a live stream right now because it's the first time that I do this and I have to merge all the cameras to the laptop, and this laptop is not that good. The Wi-Fi connection right here is not that good. I have to merge the microphone. So since it's the first time, I will have to make some tests, and for now we'll make just a podcast. And before we even start, I would like to say that I would like to change the name for this from podcast to maybe something like LearnMore or something like that, because for now the main idea of this was to invite people here, maybe other YouTubers, maybe people from my university, but it's very difficult to invite people to talk like in a podcast. So right now it's just like a theory video, so maybe I will name this like Learn More, so we'll have episodes and stuff like that. Have in mind that this will be a little bit more relaxed. This is unscripted. All I have here is just a small script of what I have to say, and this will be a little bit longer, maybe 40-50 minutes, even 60 minutes, but don't worry, you will learn a lot more. So if you have time, right now is weekend, so if you have a little bit of time, be sure that you will learn a lot more than with my normal tutorials, because I'll try to explain all the theory that we have for the ESC in this case. This is electronic speed controller. This is a very requested topic that I have. We will learn how the ESC works, all the details behind the ESC, how we detect the back EMF, how are the brushless motors internally, and how we control these brushless motors, and how we can increase the power of this ESC, because that was one of the main questions that I have on my videos. Because as you can see, this ESC, this is an open source ESC that I have. We have like 4 videos about this topic, but one of the questions that I usually have is how to increase the power of this one, because this will work only with 20 volts. But let's say that you want to use this board for an e-bike or an electric scooter, and those motors could go to 450 watts and stuff like that, and you will want to increase the voltage from 20 volts maybe to 36 to 38 or even 48 volts in case of an e-bike. So for that, of course, you can do it, but it's not that easy. So in this video I'll explain you how you can increase the power of this same schematic, but how to regulate the power, how to regulate the voltage, how to change the drivers. We'll see that at the end of the video. So before we will start, I would like to say that we have already at least 4 videos about this topic. So if you want to learn more, I will put the links below this video, and have in mind that this is an open source board. So you can go download, see the tutorial, you can download the schematic, you can download the code, the Gerbils files for this PCB for version 2. If you want version 3, which is a little bit better, is this one, which is smaller. You will find this on my shop, but this is totally free. You can download it, you can use the code, you can improve it. If you don't sell it, everything is okay for me. You can improve it, you can make your own version for your DIY e-bike and stuff like that. So go below and see these tutorials. And also I would like to take a moment and thank you to all for supporting this channel. We have already 200k subscribers. Thank you very much for that. Also to everyone that is subscribed to Electronoobs.io, which have an account to Electronoobs.io. And the most important one, I would like to thank you to all my patrons, because right now, as you all know, with the virus in China, my main sponsor is GLC PCB or LCSC, and these are in China, and right now they don't make very much sales here in Europe or China, so they will close the agreement. So we will maybe have 1 or 2 videos a month with supporting my channel. So right now the support from my patrons is very important. I'll try to put a list with all the patrons at the end of the video. So thank you very much for that, because thanks to you I can pay my rent and keep doing these videos. Okay, so let's see the topics that we'll see in this video. First of all, these are the main topics. We'll have some extra topics as well. First of all, we'll talk about the brushless motor. We'll see how it works. We'll see why this motor is considered a DC motor and not an AC motor, because a lot of you guys point me in the video that this is considered an AC motor because of the signals that we can see on the oscilloscope, but it's not like that. The mathematics behind this motor is for DC motor. We'll also see how to control it, the theory behind of how to control it, and then how to control it in real life using the triple phase bridge with MOSFETs. And I will try to explain why this is better in some cases than the brushed motors, why we use it with electric cars, why we use it with drones, how to use it as a generator and charge back the battery. Then the second topic, we'll talk about this triple phase bridge, and that's the bridge with the MOSFETs that we use to control this kind of motors. And finally, we'll also talk about the back EMF detection, how we make this back EMF detection, how we'll use the coils as a sensor, what is the zero cross detection, the common wire, and this common wire, as you can see this motor here, we have the coils and we have a triple phase input, so just 3 wires. So we don't have a common wire, but this motor here, which is from an hard drive, we can see that we have 4 wires. So we have the A, B, and C phases, and also the common wire, which is the sum of all the phases. We'll see that later in the video. We'll see how to make the internal sum, so to sum the voltages from all the triple phases inside of the microcontroller, how to use an external comparator to detect the back EMF, and how to use the internal comparator of the Atmega 328, because a lot of you guys ask me how I'm using that comparator to detect the position of the rotor. And finally, we'll talk about the PWM control, how we read the signal and how we control the speed. And we'll talk about my design, and finally how to improve this design, how to increase the power, to use it with e-bikes, and all you have to have in mind when you want to increase the power for this same schematic, because it's not that easy. You will have to change a little bit the components, the tracks and stuff like that. So okay, that being said, let's start with the podcast. So this is where we start with the theory. The first thing that we'll talk about is about brushless motors. Let me change the picture here. Okay, so we start with this representation of a brushless motor. As the name implies, this won't have brushes, so we have to change the magnetic polarity of these coils in order to rotate the rotor. The rotor is the part that moves, and the stator is the part that stays without moving. In this case, for example, this is the stator, this is an outrunner, because the outer part of the motor, which is this one with the magnets, will rotate. But the representation here is for an in-runner. That means that this is the stator that won't move, and the part that will rotate it is inside of the motor. As you can see right now, we have 6 poles and 8 magnets. First of all, these are not random numbers. You can't have like 6 poles and 10 magnets, because we need a predefined phase difference, the angle difference between the magnets and the poles in order to rotate, and we'll see that when we'll make the rotation of the rotor. So have in mind that these are predefined values. We have 6 and 8 magnets, we have 12 poles and 14 magnets. For example, this one, I think it has 12 poles, we have 12 windings, and I think here we have 14 magnets. I'm not sure right now, but we have a table with all the values and the configuration that we can make. So have in mind that these are not random, these are predefined. How we control this? Well, we apply voltages to these coils in order to change the magnetic polarity, and by that we have some magnetic, we have some permanent magnets here, so we can push it or drag the rotor, and by that we rotate it. In each part of the sequence, we activate 2 coils and we leave 1 floating. What that means? By floating, I mean we don't apply any voltage to that coil. For example, we apply positive to A and ground to B, and C will be floating, and we can use this floating coil as a sensor, because as you all know, by Faraday induction law, when we move a magnet in front of a coil, we can detect we can induce current in that coil, and by that we can create a voltage drop, and we can detect the position when this floating coil will pass exactly in the middle of the magnet. So we will see that in the back electromotive force detection part, which will be in a couple of minutes. Okay, so let's just start with applying. Let me just change here the photo. Let's just start with first I will explain how is the configuration of these coils. First of all, we have 3 phases, A, B, and C. But I know that you will say that we have 6 poles. How we can have 3 coils when we have 6 in reality? Well, that's because the coil A, for example, is divided into 2. We enter here, we wind this A coil, then we pass to the second one, we wind it and exit. So actually this is the same coil, but it's divided into 2. So even if we have 6 poles, 12 poles, 24 poles, we will always have triple phase, A, B, and C. The only thing is that we divide that coil in 2 coils, 3 coils, the phase, we divide it in 2 coils, 3 coils, and so on. So by changing the polarity of these coils, we can move it. We can wind these motors in the star configuration or in a delta configuration. Usually delta, they say, is a little bit more efficient, but it has a downside, and that's because we don't have a common connection. As you can see, we connect A, B, and C directly to the coils, and the coils are connected like this in a triangle shape. This is okay for big motors. It's okay for any kind of brushless motors, but I will explain this podcast, this theory part, only on the star shape. As you can see, we connect A, B, and C, and then we have a common connection, which is this one here. So this sometimes is called N, or sometimes it's called a COM, the common connection. So we can use this common connection to detect the position of the rotor, because by comparing the voltage on each coil when it's floating with the middle position, which is the zero value, we call this as virtual zero, we can detect the position of the rotor while moving inside of the motor. So that's very important to know that we can wind these motors in the delta configuration or star one. So by applying a voltage to these coils, we can create that magnetic field. For example, we apply positive to A and ground to B, so a current will flow here, and this will leave the C1 floating. So let's go to the next picture. As we have seen before, we have the rotor with the A, B and C faces, and then we have some permanent magnets, and as you can see, one is north, the other one is south, the other one is north, and so on. So let's, for example, start like this, and we apply positive to A and ground to B. Since the current is entering this coil and exiting the B coil, that will create a north polarity field in the A coils and the south polarity magnetic field in the B coils. And right now look close at this magnet here. As you can see, the magnet is also north polarity, so that will push this part of the coil to the right. And at the same time, this is south, because as you all know, north with north will push, and south with north will attract. So in this case, north will push this coil and south will push this south coil. But on the other side, we have north and south, so this will attract. So in this case, the north magnet will attract the south polarity coil also to the right. So as you can see, it's obvious that the entire rotor will make one step to the right. Till when? Well, till this C coil, or the coil that is floating, will pass exactly in the middle of this magnet, because that's when we detect the peak of the magnetic induction. So let's just make one step. As you can see from here, we've made one step, and exactly in this moment when we pass this magnet, we change the inputs. We have to leave one input the same, so let's say that we leave A the same, so we have north polarity in the A coils, but now instead of exiting on the B coil, we'll apply the ground to C, so we'll have a south polarity in the C coils. So in the next picture, as you can see, we don't have the south polarity in the B coils anymore, we have it in the C. So right now this magnet here, which is south, will push this rotor even more. The north will push this one, and here the south will push it, and here the north will push it. So once again, this rotor will keep rotating to the right, and it will make one more step. We go to the next picture, and that's it. We made one more step, and now we have to change another input. Since in the last one we've changed the C1, now we have to change the A1. So now the input, instead of entering through the A coil, now we have to enter to the B coil. So we change the north polarity from A to the B1. So let's see the next picture. As you can see, now we have a north polarity in the B1, so the south here will keep pushing the rotor to the right, and the north one will start pushing to the right as well. So as you can see, by changing the two polarities in these coils, on each step of the sequence we change two polarities, we can keep rotating the motor, but this is done very fast, so we don't see it when the motor spins. So all we have to do is to apply pulses to the coils, positive to one and ground to the other. And for that we'll use the triple phase bridge, and we'll see that in a moment how to use it. Okay, so as you can see, we have to follow a predefined sequence. And this sequence, as you can see, we only change the input 3 times, and we rotate maybe like 30 degrees. So as you can see, we have to make a lot of changes in order to make a full rotation. Usually this sequence will repeat 6 times, and then repeat it once again, then once again, till we complete a 360 degrees rotation. But it's very important that the sequence is made out of only 6 steps. So let's see those steps right now. For example, here we have the representation of the coils A, B and C, and this arrow will indicate the current flow. For example, we apply positive to A and ground to B. That means that we'll have a current flow through A and then through B. But through C, since we don't connect C to anything, it will be floating, so we can measure the voltage on that and detect the back EMF. But anyway, since we enter through A and exit on the B coil, the next step, as I told you, we have to leave one of the coils energized and change just the other one. For example, we leave A as it is, so we are still entering through A, but now we change the output. Instead of B, we change it to C. And in the next sequence, we leave C as it is. So we're still exiting on C, but instead of entering through A, we enter through B. So as you can see, we repeat this 6 times, and if you want to go backwards, all you have to do is instead of going like this, you have to go from this one to this one, but let's just say that we'll only rotate clockwise. So we apply these pulses, and once we finish this entire sequence of 6 steps, we repeat it once again, and once again, and once again, till we make all the rotation of the motors. The more coils, the more poles the motor has, the more times we have to repeat this exact same sequence. As you can see, in the last one, we enter through C and exit on B, and in the next one, which is this one, the first one, so we'll repeat it, we're still exiting on the B coil, as you can see, but we change the input from C to A and repeat it once again. We get here, repeat it once again. We get here, repeat it once again. And that's what I'm doing in the code. If you get the code and read each step, you will see that what I'm doing, I'm applying positive poles to A and then to B, then to A, then to C, and so on. As you can see, we have the sequence here. This arrow means that the current is entering the coil, so we have applied a positive voltage, and this arrow means that the current is exiting, so we're applying ground to this coil. So as you can see, we have A entering on A, exiting on B, entering on A, exiting on C, entering on B, exiting on C, and so on. And as you can see, we repeat it, we energize the coils 2 times. So we have AA, BB, CC. So each time that we change a part of the sequence, we leave one of the coil energized. So that's why we have AA, BB, CC, and on the other one we have CC, AA, and BB. Because we don't change 2 coils at the same time. We leave one how it is, we change the other one, then we leave this one how it is and change the other one, and so on. This is more efficient, and the motor will spin in the correct direction. So now that we know how we have the internal connection, how we have the coils, and what we have to do to control this, we will see how to actually make this, because this is just the theory behind of how to make this kind of motor rotate. But now we'll see how to use the H bridge and apply the pulses to these coils, positive to A, negative to B, and so on. But before we go there, I will also want to talk a little bit of why we consider this a DC motor and not an AC motor. Because if you look at these signals, this is the back EMF from this kind of motors. They look kind of AC because they are pretty close to a sine wave. But if we look close, this is not a sine wave, but we have a ramp, and then we have a steady current, a steady DC voltage, and another ramp. But imagine this motor will spin very, very slow. We'll have a ramp and then a lot of steady voltage, like simulate a DC voltage, and then another falling ramp. If we look at the voltages at a normal brush motor, we will see that the mathematics, if we make the integral of these waves here, we will have the same result. So the mathematics behind of the brush DC motors and the brushless DC motor are the same. These are just pulses, very small pulses of DC voltage. Also, we are using a DC battery to supply this. We apply that to an electronic split controller that will apply small amount of DC pulses to the motor. So that's why we consider this a DC motor and not an AC motor, because this is not really AC. This is actually DC. The faster the motor will spin, the closer will be this steady voltage of DC. But if we spin very slow, this will be actually maybe a few milliseconds of DC voltage. So that's why we consider this a DC and not an AC voltage. I hope that you understand. Let me just show the next image. For example, this is the representation of a brushed DC motor. This is from the last tutorial of electrical motors. And as you can see, we have 2 permanent magnets, one with north polarity and the other one with south polarity, and we have 3 faces, A, B, and C. And these are the copper pads and the brushes that will touch those copper pads. And each time that we touch these copper pads, we'll change the magnetic field inside of this winding. So for example, let's say that this time we apply a positive, we create a north polarity signal, north polarity magnetic field in phase A. So right now the brushes are touching these 2 pads. So the current inside of this coil will be the same as before. We apply positive, so the voltage in the A phase will rise. Then the rotor will spin a little bit, and the pads are now connected to the C phase. So now the C phase will rise and have a DC current. Then we apply to the B one, and then the voltage will rise, will have a steady DC voltage, and then fall back. So as you can see, if we compare the voltages from these brushed DC motors with these, which are from a brushless DC motor, they will be the same. If you connect an oscilloscope to the coils of each motor, you will get pretty much the same result. So that's why we consider this a DC motor. Okay, let's just skip this one because I don't want to lose that much time on this topic. Oh, and one more thing, we consider this to be more efficient from a few reasons. First of all, with a normal brushed DC motor, you can control the speed because, you can know the real speed unless you put a sensor or an encoder on the shaft of the motor. But with this one, since we know how much will take one pulse of each coil, and we know how much steps we need to make in order to complete a full rotation, we can easily know the speed inside of the code of our microcontroller. So for that, we use it with electric cars, because they are very much easier to control the speed with high precision. And the other one is that since we don't use brushes, copper brushes like these ones here, this will get used over time. So imagine that you have an electric car with a brushed DC motor. That means that each maybe 2 or 3 years you'll have to take the motor out in order to inspect it, in order to clean it, because the brushes will leave a lot of carbon or maybe copper, depend on the brushes that the material that you make the brushes. So you have to clean it, you have to change the brushes, and that will take a lot of time, and you have to open your car each 2 or 3 years. So that's why we use brushless motors for electric cars and drones, because you don't have to clean it that much, you don't have the copper brushes that will wear out, and so on. So that's why we consider this a better solution for our electric vehicles. Okay, so the next topic that we'll talk about is directly the ESC. So first we will see the parts of an ESC. The ESC stands for Electronic Speed Controller, and this is the entire module that will create those pulses that we apply to the triple phase input A, B, and C. So first let's see the parts that we have on ESC. The ESC structure, we have the microcontroller, that is the brain of the entire board, and will make the decisions and change the pulses that we apply to the motor. Then we have the triple phase bridge, which is usually made is always made from 6 MOSFETs, but you can have MOSFETs in parallel to have more power, but usually we use this with 6 MOSFETs. 3 of these MOSFETs are connected to the VCC, which is the positive supply, which can be 12 volts, 20 volts, 36, depending on the power that you want for your motor. And the other 3 MOSFETs are connected to ground, and the coils are connected in between of each pair of the MOSFETs. And then we have a very important part, which are the drivers, because usually the MOSFETs will work maybe at 20 volts, 30 volts, even 40 volts, but the microcontroller will usually work at 3.3, maybe 5 volts, so it's very low voltage. So in order to increase the voltage and apply very good signals to the gate of the MOSFETs, that's why we use the drivers. Because if you take a look at the curve of the current of a MOSFET, you will see that the more voltage you apply to the gate, the higher can be the maximum current. So you don't want to lose that power. You can't apply directly 5 volts to the gate of the MOSFET, only if you use the MOSFET at 5 volts. But in this case, I'm using the MOSFET at 20 volts. So that's why we need the drivers to synchronize the pulses from the microcontroller with the MOSFET gate and also increase the voltage. Let's just make a zoom on the triple phase bridge, because this is not that important. These are just some ICs, some drivers, and this is the microcontroller, which is the Arduino, the Atmega 328. So let's just make a zoom on the triple phase bridge. This is the basic representation of a triple phase bridge, and as you can see, as I told you before, we have 3 MOSFETs connected to VCC and the other 3 are connected to ground. And the phases of the motor A, B, and C, A with the red, B with blue, and C with green, are connected in between of each pair of MOSFETs. So if we want to apply a positive pulse to each of the coil, we activate the MOSFETs that are on top. So imagine these are just switches. So if you want positive, you enable this one, and if you want connected to ground, you enable this one. So let's just say, as before, we want to apply a positive pulse to A and ground to B. All you have to do is to activate the top side MOSFET of the A phase. So positive will be connected to this red one, which is phase A. And all you have to do then is to activate the bottom MOSFET of the B phase. So now the B phase is connected to ground. The other 3 MOSFETs or 4 MOSFETs are not connected to anything. So the current will flow from VCC, then will go to this MOSFET here. Then we'll go to the A side of the motor, we'll pass the entire motor and get back from the B coil. Then we enter the B coil, and when we get here, since this MOSFET is turned off, we can go back to VCC. So then the current will go back to ground because this MOSFET is also activated. So look how easy it is to control the pulses that we apply from the sequence that we have seen before. So for example, you apply positive to A and negative to B, then you read positive to A and negative to B to C, and so on. All you have to do is to enable 2 MOSFETs on each part. We only have 2 MOSFETs activated on each side, and the rest are not connected. So we can use the last coil that is floating and detect the voltage. For example, if you apply positive to A and negative to B, the C here is these MOSFETs are turned off. So the voltage here will be floating. we can read that voltage, and we will read the voltage that is coming back from the coils. I hope that you understand this. This is pretty easy to understand. To apply the pulses to the coils, all we have to do is to enable one MOSFET from the top side and one from the bottom side. Depending on the phase, you can enable A with B, maybe A with C, B with A, and so on. I think it's pretty easy, and to enable these MOSFETs, all you have to do is to apply a voltage at the gate, and we do that with the microcontroller and the drivers we have seen before. Okay, so now we know how to control this H-bridge and how to make the real connections to the motor and make the real sequence that we have seen before in the theory part. So now we know how to control this. The next part is to know the back electromotive force. And why is that important? Well, first of all, because the changes from one phase to the other is not random. We can't make it in any given moment. We have to make it exactly when the rotor is in the given position, because otherwise the motor, while spinning, could spin to the right, and then if you don't make the change when it's needed, it will start spinning to the other side, to the left, for example, or even get stuck in the same position. So it's very important to make the switch in a very specific given moment. And for that we need to know the right position of the rotor. And to detect the position, we could use an encoder or a sensor. We could use Hall sensors, but the other option is to use the back electromotive force as a sensor. So let me just explain you how this back electromotive force works. Let me just change the picture here. Okay, so by the Faraday law of induction, we know that when we pass a magnet in front of a coil, so these magnets from the rotor, when they pass in front of these coils, they will induce a current inside of the coil using that back EMF. So if we have a current inside of the coil, since the coil will have a small resistance, they will create a voltage drop at the output. Since we have two coils activated, energized, and the other one is floating, we can read that voltage drop on that floating coil. And that will detect when we are passing in front of the magnet. Okay, so for that, here I have a representation of a magnetic field of this magnet. Of course, each of the magnets will have its own magnetic field, but let's just look at this one. So remember at the beginning, I've told you that we have to make the switch from one phase of the sequence to the other one when the floating coil is passing exactly in the middle. And how can we detect that middle position of the magnet? Well, as you can see, the magnetic field here is not that big. We have a very large space between the magnetic arrows, between the magnetic field. But as we go in the middle of the magnet, the magnetic field will be more compressed. So the magnetic flux inside of the coil will be bigger. So when we move the coil in front of the magnet, what we'll see a voltage peak exactly in the middle of the magnet. So we can detect that voltage peak by connecting the signal to a comparator. And when we detect that voltage peak, we will have a positive output from the comparator. We connect that to the microcontroller, and by that we detect the position of the rotor. So let me just change to the other picture. Okay, so as you can see, let me just... Okay, so we still have the magnetic field. Let's just say that we apply positive to A and negative to B. So we have a north polarity here and a south here. And then this C1 is floating. So as we are moving to the right, the C coil will pass exactly in the middle. And in the next picture, as you can see, we have the magnetic fields. And here, right here, we have this arrow. And that means that we use the C coil as a sensor by detecting the magnetic field of this one. If we apply a positive to A and negative to C, well, the B will be floating, and in that case we use the B coil as a sensor. And if the A coil is floating, well, we'll use the A coil as a sensor. So all we have to do is to measure the voltage on this floating coil and compare it with the common voltage and that we have seen before, which is the COM voltage, which is the all the voltages of all coils merged together. It's the sum of all the voltages of all the coils, and we can have that voltage with the common wire here, which is the real connection to the middle of the windings, or we can make another common mode that we have to merge the voltages on the phases A, B, and C with resistance, and the sum of all those voltages will be our zero value. So all we have to do is to compare the voltage on the C coil, on the floating coil. In this case is the C1, but it can be the A or B. So we compare that voltage with the zero value, with the virtual zero value, and when we pass that voltage by rising or falling, we can make the switch to the next sequence. Let me just change to the next photo. Okay, so how can we measure this voltage? Well, a very good way is to use comparators. So we connect the floating coil to the positive input of a comparator, which is just an op amp, and then the negative input is connected to that COM value, which is the virtual zero. We'll see this virtual zero just in a few moments, but just have in mind that this is the steady value that we'll have to compare. When the voltage on the C coil is higher or lower, and exactly when we make the cross of the COM value, we'll make a switch. For example, if the floating coil is higher, we'll have a 1 at the output, and if it's lower, it will have a 0. In this case, we have a 1 because, for example, the C coil is higher than the COM value, and we'll have a 0 and a 0 for B and A. If the A coil will be floating, we will take a look at this op amp here. But since we are using the C coil right now as a floating coil, we take a look at the C op amp here. So the output from this, while this rotor is spinning, will be 001, 010, 101, and so on. So by reading these digital outputs, because it's very easy to read the digital outputs with a microcontroller, we could know the exact position of the rotor and know exactly when to make the switch to the next step. Now let's just talk about a little bit about that COM value. That COM value, as we have seen before, it could be from this middle, the union of all the coils, which not all the motors will have. In this case, this motor has 4 outputs, so we have the A, B, and C, and also the common value. But usually for this kind of brushless motors, we only have 3 inputs. So how we can read the common value? Because we can merge together the inputs, that will be a short circuit. So all we have to do is to add some resistance, one resistor to each input of the coil, and the sum of this resistance will give you our common value. Because, for example, this is positive, this is negative, and this is floating. If we sum the voltages of each of these coils, we get our common value. Okay, but have in mind that the resistance of these resistors must be very high, because you don't want to have a huge current passing through these resistors, because we are not measuring current, we are measuring voltage. So maybe place these resistors at 30k or maybe 40k ohms. So in that way you make sure that we won't have a huge amount of current passing through these resistors. So that's how we do it. On this PCB here, these are the pads, the A, B, and C outputs. So on this schematic, you will see that we have 3 resistors connected to each of these A, B, and C outputs. And then we merge these resistors together and we get our common value. And then we get back to the op amps and connect the common value to our op amps, and then we take a look at each of the floating coil, and when we detect a change from 1 to 0 or from 0 to 1, we know that we have to switch to the next part of the sequence, and we'll have a lookup table with all of the outputs from 001, 010, 101, and so on. So in that way we can know the exact position of that sequence, of the sequence that will repeat each 6 steps. Okay. So now we know how to get a common value, and now we know how to use the op amps to compare the outputs. But in order to know why we switch exactly when we pass that 0 value, that virtual 0, we have to take a look at the back EMF from the motors. This is a representation of the back EMF from the motors, so this will be the signal that you will see if you connect the oscilloscope to the output of the ESC when it's connected to a brushless motor. And here we have the pulses that we are applying to the coils. As you can see, this is an electrical cycle and this is another electrical cycle, so each one of these is a 360 degrees rotation. So we have those 6 steps that are repeating from the sequence: step 1, 2, 3, 4, 5, and 6. Let's just look in the first step. In the first step, on the back EMF, you will see a rising ramp of voltage in the positive side and a falling ramp in the positive side as well. And then you will see a totally negative voltage. To understand better, let's just say that positive is +1, negative is -1, and floating will be 0. So exactly in this step here, a positive rising ramp with a positive falling ramp will make a +1. So we have +1. If we sum +1 with a -1, we get the 0 value. So in this exact same step, if we sum all the voltages on A, B, and C coils, we get our 0 value, which is called virtual 0. It doesn't have to be a 0, it doesn't have to be ground, it will be a steady value that we call our virtual 0. We go to the next step. In the next step, what do we have? We have a +1, because this is fully 1, this is fully positive, and then we have a falling ramp, but on the negative side, and also rising ramp on the negative side. So one falling ramp on the negative with another rising ramp on the negative will give us -1. If we make -1 +1, we get another time the 0. Let's just make, and that will be our COM value. Let's just make a zoom, and as you can see on each step of the sequence that will repeat after 6 times, step 1, 2, 3, 4, 5 and 6, on each step we have the signals in such a way that if we sum this positive ramp with the negative ramp, we get a 0 value, because rising ramp on the positive, falling ramp on the positive with totally negative, we get the 0. The same on this one, the same on this one. So as you can see on each step, if we sum the values, we always get our 0 value, which will be our virtual 0. And what's that? Why is that important? Because as you can see, when the voltage is passing this exact 0 value, this point here, this point here, this point here. So when we have the cross of the 0 value, that's why this technique is called zero cross detection. When we detect this 0 cross, when the op-amp goes from 0 to 1 or from 1 to 0, because we can have the cross from falling edge or from rising edge. For example, here the op-amp that is connected to the C coil will go from 1 to 0, but here will go from 0 to 1. So exactly on these points here, we have to make the switch. As you can see, the line of the step is exactly on this point. So that's why we first have to calculate this sum, the 0 value, and then we have to detect when each of the phases will pass that value, and then we make the switch. How we do that? Well, with op-amps, or we can do it directly by reading the voltages here, make the sum, and then compare each of the voltages with the total sum. So let's just go to the next picture, because one of the questions was how is my board not having 3 of these op-amps? These are operational amplifiers. Instead of using external op-amps that will occupy a lot of space on the board, what I've done, I've used the operational amplifier, this one, that the Atmega 328 already has internally. And this is a programmable op-amp, and that means that you can program the inputs. The input from the positive side is always connected to pin D6, which is a real pin of the microcontroller on the board. So on this pin D6 we have to connect the common value, because the common value, which is the output from those 3 resistors, which is this output, we connect this to pin D6. We connect this to pin D6, which is the positive input of our programmable comparator, and then we have a multiplexer, a MUX. So by changing some registers in the code, we can select which of the ADC0, ADC1 or ADC2 or the other ADC are connected to the negative input. So for example, if the floating coil is the A, all we have to do is to change the registers in order to connect the ADC2 to the input of the comparator. So in this way, using just one comparator, we can compare all the three signals. We don't need 3 comparators. And the best of all is that this is already inside of the microcontroller, so we don't have to use extra space on the PCB. And it's very easy to control it. All we have to do is to change some registers. And each time the output of this comparator will go from 0 to 1 or from 1 to 0, it will enable an interruption, an ISR. And we go into the vector of that interruption in the code, and we'll make the switch. If the output was 001 or 100, depending on the sequence that we are, we change to the next step. For example, if the A was high and B was low, and C was floating, we change to the next sequence, which A high and C low, and so on. So using interruptions is very easy to control the code, because what the interruption will do is, while you are making the full loop of your code, when we detect an interruption, we pause that part of the code, we make the changes in the interruption, and then we keep with the loop. And so in this way you can always detect the change. You can skip it with the interruptions. That's the good part. So that's how I use the internal comparator from my board in order of instead of using external comparators. I hope that you will understand this. This is taken from the datasheet of this microcontroller. You can download it from below if you want to take a look at it. All you have to do is to change these registers, the ACBG, the register for the AC/DC multiplexer, and here I have a small part of the code. I hope that you will be able to see this, and if not, I will try to put the entire photo for a few seconds on the screen. But as you can see, we have 6 voids. Here we have only 4, from A rising, A falling, B rising, B falling, and we will have here the C rising and C falling. But as you can see, in each of the void, all we are doing is to disable the ADC. Then we make the MUX the negative input of the MUX connected to D6, and then the positive input of the MUX AD MUX is equal to 2. That means that the AD, the positive part of the comparator, will be connected to ADC2. So we are reading the back EMF from the A coil. And in the falling we do the same. All we have to do is to set the interruption from rising edge to set the interruption for a falling edge. That's the only difference. And then on the void from back EMF B rising, the only difference is that instead of the AD max equal to 2, we change the AD max equal to 1, which is connected to the back EMF from the B coil. And for the C, it will be AD max equal to 0, which is connected to the back EMF of the C coil. So read this part in the code to understand more, but all we have to do to control that comparator is to change these lines here of these registers. Okay, the next part is another part of the code. I'll try to put it once again on the screen when I'm editing this, and are the voids that I'm using to switch the pins, to switch the signals that are applied later to the drivers to control the MOSFETs. So all we have to do is to turn one MOSFET from the positive side to high and the other MOSFET to low to connect it to ground. So as you can see, for example, when A is high and B low, so A high, B low, we make the port D, which are the pins from 0 to 8, I think, yes, the pins from 0 to 8, we set that 1 to be high and a 0 to be low, so A is high and B low. Then A is high and C is low, B is high and C low, and so on. We'll have 6 of these voids. So read this in the code in order to understand more, but all we are doing we are changing the port output to be high or low and create those signals for the sequence of the 6 steps. And not just that, but we apply a steady pulse to one of the MOSFET and the other one, which is connected on the bottom side of the bridge or on the top side. I don't remember right now. One is a steady DC voltage and the other one is a PWM signal in order to control also the current that is passing through the coil. So we energize it and then we disenergize it. So that's why we use the TCCR1, which is the time compare register for the PWM signal. So we change it to enable or disable this PWM signal. So one pulse is steady and the other one is PWM to control the current that is flowing through the MOSFET as well. Okay, and the final part, which is the part that we've talked before, is how to make the PWM read in order to control the speed. Usually this kind of ESCs are used for drones or RC toys, and these are controlled with the PWM signal that you get from the radio receiver. But if you would like to make an ESC for an electric bike, as you all know, for the electric bike, in order to control the speed, you are pushing a control, which is actually a potentiometer. That is very easy because, as you can see here, we have a potentiometer, and all you have to do to control the speed is to read the value of that potentiometer, which is an analog read, and then pass that to milliseconds or to microseconds, which will represent the difference of the phase for each step. The bigger is the pulse, the slower the motor will spin. The smaller is the pulse that we apply to the coil, the faster the motor will spin. But in this case, in order to read the PWM signal, which is just a signal that will change its width, so it gets high, then it will change the width and it gets low. In order to read that, all we have to do is to make an interruption. So each time that this signal will change its values from 0 to 5 volts, which is high and low, which is low and high, we make an interruption. So for example, the signal is steady, is low, and then we have the rising edge. On the rising edge, we enter that interruption and we save the current count to micros. So we save the current time. And then when we get the falling edge, we get another interruption and we save once again the time. So if we make the time difference between the first interruption and the second one, if we make the difference between these two values, we get the width in microseconds of the pulse. I think that is very easy because when we detect it to high, we save the state. When we detect it to low, we save the second state and we make the difference. So the PWM input is equal to the current count, which is the state right now, minus the counter 1, which was the state at the first rising edge. And then we pass this PWM input to microseconds, or depending on the speed that you want, to nanoseconds. And those will represent the time that you will enable each of the steps of that sequence, of the 6 steps of the sequence. So of course, the bigger is the time, that means that more time will take each step, so the motor will spin slower. The smaller is the time of these pulses, the faster the motor will spin. I hope this will make sense. Okay, so finally we'll talk a little bit about my design. Let me just change the picture here. Okay, so this is the schematic from this second version. No, this is for version 3, which is this one. The schematic is pretty much the same for version 2 and 3. I think small changes maybe in the resistors or the pads, but anyway, I'll try to put a picture with the schematic so we can take a look at this. First of all, let me explain the parts that I have on my design. First, we have a power block, and this power block will make the regulation voltage for the IC, because as you all know, the input for this ESC will be from 12 volts to 20 volts, but the microcontroller, which is this one here, can work with a voltage of 5 volts. So in order to use it, we have to lower the voltage from 20 volts to 5 volts. You can use an LDO or a linear voltage regulator, but that is not recommended for this kind of ESCs that you will use with drones, because you want to make the power regulation as efficient as you can. Because you want to save power, you want to save battery for your drone. So that's why instead of an LDO, I've used a buck converter to lower the voltage. So this is a buck converter IC with a coil and some resistance that will give exactly 5 volts at the output. This is a much more efficient, and it won't get hot, because an LDO at this power from 20 volts to 5 volts will get very hot. You need a heat dissipator, you need to occupy a lot of space on the board, so it's a lot better to use a buck converter. In case that you are making a big ESC, for example for an electric bike, a small voltage drop of a small power loss of the LDO is not that important. So if you want to make an ESC for an electric bike, you can use an LDO, but in my case I've selected a buck converter for this very small ESC. The next block is the Atmega 328P AU. This is the microcontroller that I'm using with the crystal, with the pull up and the button. No, I don't have a button in this case, and all the inputs and outputs. Then we have this triple phase bridge block. We have the MOSFETs, the 6 MOSFETs, each pair, and each one with a driver, because this one is a double driver, a dual driver, so it can control 2 MOSFETs at the same time. This is the IRL 2101S. This is a very good driver. It's connected to the MOSFET, so we can control the outputs, and the input of the driver is connected to the microcontroller. A very important part is this part here, and this is the back EMF voltage driver dividers. And these are the dividers that are coming from the back EMF. And why we need these dividers? Well, that's because the voltage value of the microcontroller is a maximum of 5 volts. But the back EMF that we get from the motor, since we are supplying this motor with maybe 20 volts, it could be above 20 volts. So that voltage will burn our ADC of the or the comparator of the microcontroller. So in order to connect the voltage from the motors, which is very high, to the voltage of the microcontroller, which is very low, we need to lower the voltage, and that's why we use these voltage dividers. In this case, I'm dividing it with a divider of 10K divided by 33K, so it's 10K divided by 43. So maybe from 12 volts or 20 volts, we can get to around 3 volts, which is below the maximum voltage of the microcontroller, which is 5 volts. And the last blocks are the Warten SPI pads, and also the main input and the PWM. This is the main input for the 12 volts or 20 volts in this case, and the PWM input for the signal to control the speed of the ESC. Okay, so right now we know the blocks that we have. We have the drivers, the back EMF voltage dividers. Let's just talk how you could improve this schematic, how to increase the power. First of all, if you ever seen an ESC for an e-bike, you would see that it is enclosed in a big case that is made out of aluminum, and that's because the power dissipation inside of that box is a lot bigger than this one. So first of all, you need to dissipate a lot of heat. But before that, one of the most important part that you will need to change from this schematic is the voltage divider values. The voltage divider is the same, but the resistance value will have to increase. And that's because instead of 20 volts in this case from the back EMF, you will have maybe 38 volts or even 48 volts. So that will definitely burn your ADC. You will burn the microcontroller. So what you have to do is to increase the voltage dividers. Maybe instead of 10K and 33K, you will use 10K and maybe 150K. So in that way you make sure that the voltage that is coming from the motor is always below 5 volts. Just so you can read that with the comparator that we have inside of the microcontroller. So first step that you want to make to increase the power of your ESC is to increase the resistance, the division value of this voltage divider. Okay, the next step is the power regulation here. As you can see, I'm using a buck converter and I'm only getting from 12 volts or 20 volts to 5 volts. But when you will increase the voltage to 48 volts, what you will see is that the MOSFETs will be connected to 48 volts that will go to the motor, but the drivers, the maximum voltage for the drivers is 24 volts. And also the maximum voltage for the microcontroller is 5 volts. So you will need 2 parts of voltage converter. So you have to get from 48 volts to 24 volts for the drivers, and from 24 volts to 5 volts from the microcontroller. So you have to have these steps 2 times, and maybe instead of using a buck converter you could use a linear regulator, because when you have a big case you can put a huge heat dissipator on top of the regulator so it won't burn. And also with maybe using the LM317, that will be a good option. You can get very steady voltage for the drivers and the MOSFET. Or maybe instead of using drivers you can use directly a BJT connected to the main voltage, but that will change a little bit the schematic. Also have in mind that the maximum voltage that you could work with these drivers is 24, and you will be using the MOSFETs at 48, so the voltage applied to the gate is not exactly the same, is not the same value as the voltage applied to the drain of the MOSFET, and that would create problems. So for now all you have to do is to change the voltage divider's value and then change a little bit the power block, because you will need 2 voltages. Well, 3. The main input of 48, the second input for the dividers for the drivers of 24, which is the maximum voltage, and the third value of 5 volts for the microcontroller. So that's what you will need for this for the power regulation. And finally, to increase the power of this entire schematic, what you could do is to increase the power of the MOSFETs. So instead of maybe a MOSFET with a current limit of 50 amps, you could add MOSFETs of a current limit with 200 amps. Or another thing that you could do is instead of placing just one MOSFET, maybe place 2 or 3 MOSFETs in parallel and control the gate of those MOSFETs at the same time. So in that way the resistance will be lower, so you could have a much higher current flow to those transistors. I haven't tested this yet, but right now I'm working on a project for an e-bike electronic speed controller. I'm not sure when I will finish that board and receive it from China, because right now GLC PCB are having a little bit of delays. But when I have all the tests made, I will share that with you. If you want to test it in your workshop, just take this schematic and, as I told you, change the dividers, change the power regulation, and maybe add a few more MOSFETs here. Another thing that you will have to have in mind if you want to increase the power is that by increasing the power you increase the temperature that you will be dissipating from the MOSFET. So very important is to add huge heat dissipators. That's why the ESCs from those electric bikes will have all the case made of out of aluminum, and the MOSFETs are directly glued with a thermopaste to that case in order to dissipate all the heat. And you can even you could even place a cooling fan to keep the components very cool, because with this much power for a motor of 450 watts, you will dissipate a lot of heat. So you can place MOSFETs in parallel. You can make a separate voltage divider. You can add more MOSFETs in parallel. You have to add heat dissipators, maybe even a cooling fan. And another thing that you should do is to make the tracks of the copper tracks on the PCB a lot thicker, because as you can see here right now on the third version, the tracks are exposed, so I could add some solder in order to withstand much current. But even so, these tracks are only 3 mm thick, so we'll have to make bigger tracks because the copper thickness on the PCB is not that thick. So maybe with 100 amps or 150 amps, those tracks will burn out definitely. So what you want to do is to make the tracks a lot thicker and even expose those tracks so you could fill those with solder, and by that they could withstand a lot more current. So that's what you should do if you want to increase the power of this schematic. Change the voltage divider, change the power control, be sure that the voltage that the drivers can apply to the MOSFETs is good. Also, you can add more MOSFETs in parallel to increase the power. And very important, to add heat dissipators to each of the MOSFET and also to the LDOs, and maybe even a cooling fan, and make the tracks a lot bigger so they could withstand a lot more voltage. The rest of the schematic could be the same, but have these things in mind. So that's pretty much what I have to say about improving this schematic. The last part of this is the future improvement that I want to make for this ESC. The first one is to add a potentiometer control, and that is very easy. It's a lot more easier than controlling with the PWM signal, because all you have to do is to add a potentiometer input. Maybe for the fourth version of this ESC, we'll have a separated pad, and then we can connect a potentiometer to that pad. And by reading the analog value of that potentiometer, we can change the speed. It's a lot more easier than creating an interruption, detecting the time differences, make the difference between the rising time and falling time, and then get the PWM width, the value, and then pass that from microseconds to the speed of the motor. So yes, that will be one of the the improvement that I want to make for this PCB to add a potentiometer control in order to use it with those e-bikes controllers, because that is just a potentiometer that will change the analog value. Another improvement that I want to make is to make a better version of the firmware, because I have some small steps in the code that are having some troubles. For example, when we first start the motor, we have a loop that will create the first rotation of the motors. So that loop is always predefined, is not controlled with the PWM for the speed, so we'll have to make some changes there, maybe use more the EEPROM memory of the chip to save more values, for example for the configuration, to save the maximum speed and the lower speed, to maybe even have some modes in the firmware. So that will be also an improvement that I want to make. And one of the best improvement that I could make is to use an STM32 microcontroller instead of the Atmega 228, because the STM is a lot more powerful. It could work at higher powers, at higher speeds, but for now I don't have enough knowledge for the STM32 because I haven't used it that much. And the most important part is that the code that I've made is all based on registers. And those registers, you have to read the entire datasheet of the Atmega to know how to use that. So since I haven't used the STM32 that much, I'll have to gather all the knowledge that I've gathered these last years with the Atmega 328 once again for the STM32. I have to make tests, I have to see how to control the outputs with registers for the port D, for port C. I don't even know if the STM32 has an internal comparator, so I will have to look that out as well, or maybe even use external comparators on the PCB. So that's why for now I'm not using the STM32, because I don't have enough practice with this microcontroller. So that's it. I think this is where the podcast will end. Well, I already told you that I don't want to call this a podcast anymore, but this episode, this Learn More episode will end. I'm not sure if I will change the name to that. Once again, I hope that you will learn something new. I hope that this will give you a general idea about how to use the electronic speed controller, because we now know how to control the brushless motor, the internal configuration of the brushless motor, how to apply the signals and control the rotation speed, how to use the triple phase bridge, how to control the triple phase bridge with the microcontroller and the drivers, the back EMF detection, what is the zero cross, how to get that common value, why we make the switch exactly when we pass that zero cross, and so on. So I hope that now you have a general idea about ESCs, because I had a lot of questions on my ESCs videos, and I hope that you will learn something new. Thank you very much for your support on Electronoobs.io. If you made an account, on all my accounts on all my YouTube channels, the Spanish channel or the English channel, depending on